Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In the previous video, we were dealing about organic compounds. So continuing the series further, in this lecture, we will see the classification of organic compounds. Okay, so organic compounds are broadly classified under two headings. One is acyclic and cyclic. Acyclic, as the name suggests, opposite of cyclic. That means if cyclic compounds are ring compounds, then acyclic compounds are open chain compounds. So all the open chain compounds fall under the category of acyclic compounds, and they are also called as aliphatic compounds. Okay, they form straight chain or branch chain, whose nomenclature we have already dealt in the previous lectures. Okay, so we are basically dealing with the nomenclatures of aliphatic or the straight chain hydrocarbons, and they fall under the category of acyclic or open chain hydrocarbons. Okay, next the other is cyclic or closed chain. They basically contains rings. Okay, so the cyclic can be further classified into two categories. One is alicyclic and another is aromatic. Okay, alicyclic somewhat derives its names from aliphatic plus cyclic. Okay, so aliphatic compounds were the straight chain compounds, right? So if I'm removing, suppose I'm having a five membered chain of carbon, and the end groups are CH3 and CH3. So if I'll remove two hydrogen, one from one CH3 and one from the last CH3, and I'll basically join them together, they form a ring of all the carbon atoms connected with a single bond. They are called as alicyclic compounds. Okay, if there is an alkene also, then the same thing happens. If I'm removing the two hydrogen from ends and I'm joining the carbon atoms together, they come under the category of alicyclic hydrocarbons or alicyclic rings basically. So alicyclic compounds are further classified into homocyclic and heterocyclic. Now what do you mean by homo? Homo somewhat similar, like symbolizes same, right? So if in a carbon ring or in a chain all the atoms are carbon and hydrogen only, then they fall under the category of homocyclic. So basically homocyclic compound, if I'm giving an example, then this is cyclohexane. Here all the like atoms present in the ring are carbon and hydrogen. That's why it falls under the category of homocyclic compounds. Now you might have remembered in the previous lectures I have said something about hetero atoms. What is that? So any atom other than carbon and hydrogen in the carbon ring or carbon chain are called as heteroatom. So if there is any other foreign atoms which does not belong to the family of hydrocarbons, they form heterocyclic rings. So if I have to cite an example of heterocyclic, then I can say this, its name is tetrahydrofuran, THF, which in further lectures you will find out that THF is used as a solvent for organic reactions. So if I have to give an example of heterocyclic compound, then THF is an example where despite of carbon and hydrogen, there is also the presence of a oxygen atom in the ring. Okay, next is aromatic. So aromatic is a whole like branch of chemistry. There you have to study, not branch of chemistry, branch of organic chemistry, where you have to study about various specific reactions of aromatic compounds. You have to test the aromaticity of compounds. So for now we will be dealing it in detail in the further lectures, but for now remember, aromatic compounds are those cyclic compounds which satisfy certain conditions. Now what are the conditions? First is they must obey Huckel's rule. Okay, now what is Huckel rule? Again, that question might be arising in your mind. So Huckel rule, for the time being, remember they must have 4n plus 2 pi electrons. But what is that and how to exactly calculate them, we will be taking up in our next upcoming lectures. Okay, where we'll be dealing about aromatic hydrocarbons. So remember, they have to satisfy Huckel's rule. Second is they must be planar. Okay, all the atoms of the ring must lie in one particular plane. And next, some very important condition for them is they must be showing conjugation. They must be showing conjugation, or you can say they have to show conjugation in order to be aromatic. Now what is conjugation? Again, we will take up further, but for now remember, conjugation is the presence of alternate single bond and double bond. Okay, conjugation is the presence of alternate single as well as double bonds. So for a compound to be aromatic, it has to satisfy the following conditions. It has to satisfy Huckel's rule, it must be planar, and it has to show conjugation. Okay, so though the compounds satisfying these characteristics fall under the category of aromatic hydrocarbons. Again, aromatic hydrocarbons are ring compounds. They are further divided into two categories. One is benzenoid and non-benzenoid compounds. Now see, if I'm saying aromatic, a time will come whenever I'll be saying aromatic, one particular compound will be coming to mind, and that is benzene. Okay, so benzene is the hero of aromatic compounds. So I can say what is the structure of benzene. I guess I have discussed in the previous lecture, but still I'm saying it again. If I see the structure of benzene, it's a 6 carbon atom compound where there is presence of alternate single bond and double bond. Okay, alternate single bond, double bond, single bond, double bond, single bond, double bond, and single bond. Okay, this particular condition is called the case of conjugation. Here benzene is showing conjugation. Now if you have to calculate Huckel's rule, if whether it is obeying the 4n plus 2 pi electrons or not, or whether it is planar or not, those things will take up in our further lectures. Okay, so for now remember, if any compound is having this in its structure, then that falls under the category of benzenoids, and anything which deviates from this structure falls under the category of non-benzenoids. If I have to give an example, benzenoid, for benzenoid the best example is this benzene. Okay, what can be the best example than benzene itself, right? So the next for non-benzenoid is, if I'm saying furan. Okay, this is the structure of furan. Now if I'm adding 2 moles of hydrogen to it, then these two double bonds are getting broken down. Remember addition reaction in the previous lecture, and we are getting tetrahydrofuran. Okay, tetrahydrofuran. If I'm adding 2 moles of hydrogen, that means 4 hydrogen atoms. They are getting added to these pi bonds respectively. Those pi bonds are getting broken down and they are converted to single bonds with hydrogen. They form tetrahydrofuran. Okay, so furan is a non-benzenoid compound. Some other example also if I have to give, then okay, thiophene. This is the structure for thiophene. So these were some examples of non-benzenoid compounds. So in the overall classification, if I have to classify organic compounds, I will classify them into 2 broad categories. One will be acyclic and another one will be cyclic. Okay, acyclic and cyclic. Acyclic means they are open chain compounds, they are not ring structure, they can be straight chain or branch chain. Okay, that depends. And we have dealt with their nomenclature individually in the previous lectures. If you have not seen that, you can go back to the lectures and first understand them, then you can come back here. Then one was that broad classification, and the second is cyclic or closed chain compounds. They contains basically ring. Okay, and ring can be of 2 types. They have to be alicyclic or they can be aromatic. What is alicyclic? Alicyclic has derived its name from aliphatic compounds. Those are cyclic. Okay, initially they were aliphatic compounds, but after I have just connected the carbons from end to end, they gained a cyclic structure. They fall under the category of alicyclic compounds. And the next is aromatic. For a compound to be aromatic, it has to satisfy certain set of conditions, which is Huckel's rule. It has to be planar and it has to show conjugation. Okay, what is that? We have seen in case of benzene. I have just explained conjugation through an example of benzene, but the other points we will go in detail when we are in need of that. Okay, for the time being, the aromatic compounds are classified into 2 categories. One is benzenoid and another one is non-benzenoid. What are benzenoid compounds? Those contain, okay, benzenoid basically means those contain benzene ring in it. Okay, so those fall under the category of benzenoids. But apart from benzene, if there is some another heteroatom in the ring and that becomes or that satisfies the condition of aromaticity, then they are also categorized as non-benzenoids. Basically, non-benzenoids are aromatic compounds but not purely containing all the carbon atoms in the ring. Basically, see here example, if I'm saying furan. Okay, furan also, let me clear this for you. If I'm saying furan, This is the structure for furan, and we know oxygen has two lone pair of electrons. So now whether here we have to check whether it is having conjugation or not. Basically, conjugation means alternate single bond or double bond, but in addition to double bond, negative charge, positive charge as well as lone pair are also utilized or can be used for extension of conjugation. Okay. For example, here if I see basically pi electrons or negative charge, that means electron density, right? That electron density can be in any form. They can be pi bond, they can be negative charge, they can be lone pair of electrons. They just have to keep the trend of double bond, double bond and single bond going. Okay. So here what it happens is, here I'm getting a single bond, double bond, single bond, but here despite of the double bond I'm getting what? Lone pair of electrons in conjugation. Okay, so these lone pairs of electrons on oxygen are also useful in extending conjugation to the next carbon atom. So basically I can say here there is presence of alternate pi bond, lone pair and pi bond. Okay, single bonds are there obviously, but lone pair chain is broken by a the pi bond chain is broken down by the presence of a lone pair. So therefore I can say furan is also a non-benzenoid ring and it is aromatic. Okay, non-benzenoid, they are aromatics only, but they have some other like heteroatom apart from carbon. I hope I'm clear. Okay. The next thing, here we have dealt with a broad classification of organic compounds. Now in today's lecture, I'll be giving you a brief idea about how organic reactions are actually carried out, what are the mechanisms of organic reactions, or what are the basic foundations required for understanding the mechanism of organic reactions. And from the upcoming video, we will take up the mechanisms in detail. Okay. So why are mechanisms what are mechanisms and why are mechanisms important? We'll be seeing further. Let's see. Firstly, you have to see next is fundamental concepts which you have to require for understanding any organic reactions. Okay. So before moving to organic reactions, let us take up any chemical reactions for that matter. Okay. Suppose I'm saying A and B are my two reactants. They are converting themselves to product C and D. Okay. A and D were my reactants. Reactants are those species reacting with each other. So A and B are my reactants. They reacted with each other. They gave rise to product C and D. So you cannot expect that immediately I'll put A and B in a reaction medium or a vessel and they will directly give me C plus D, right? No, it will take some time. Now what is happening in that interval of time? Meanwhile, when I'm adding the reactants and I'm getting the product, in between that transition phase, what is happening? My reactants are colliding among themselves. There is collision. They attack themselves. Then they older bonds are broken down and newer bonds are formed. Right? Basically, this thing is happening. So same is the case of organic reactions. Considering inorganic reactions or in general any organic or any chemical reactions, organic reactions are no exception. Here what I'm taking, I am just giving or assigning specialized name to my reactants. Okay. Reactants in organic can be classified into two categories. One is organic molecule, which is known as the substrate, and the other is reagent. Now what is substrate? Substrate is that part which is under study, okay, which is important to us, or substrate is that part of the compound which donates its carbon for forming the bond. Okay, so substrate is that organic molecule which gives its carbon for forming a new compound. And if both the cases, if substrate and reagent both are having a carbon atom, then the choice of substrate is based on our focus of study. Whatever compound we are studying, whichever compound we are paying attention to, that becomes our substrate. On the substrate, something comes to attack, that is known as attacking reagent. Now substrate and attacking reagent, they react with each other, they combine with each other to give a transition element or the transition compound which is known as intermediate. So my organic molecule was known as substrate. Okay, substrate is that molecule which is under study, or I can say that molecule or that compound which basically lends its carbon for forming the new organic compound. Got it? So substrate reacts with an attacking reagent, or why I'm saying attacking reagent? Reagent is something that comes to attack the substrate molecule. Okay. After the reagent attacks the substrate molecule, there is breaking down of bonds and something. Then they reach an intermediate state where they lead to a unstable complex or a short-lived species basically that lives for a short amount of time, and after that further rearrangement takes place and I'm getting my products. And along with products, I will also get some side elements which are side compounds which are not necessary for me. Those are called as byproducts. Okay, byproducts are not under my study. I'll basically be focusing on products. Okay, products are what? Products are that substance which are basically required for us. In a substrate and reagent reaction, I'll be focusing on the products, not the byproducts. Okay, so this is how a general organic reactions will be looking to you. There will be a substrate molecule, that is an organic molecule which lends its carbon for formation of bond, and if both the organic molecule as well as attacking reagent are giving their carbon or combining their carbon together, then substrate will be arbitrarily chosen basically on the focus of my study. On which molecule I am focusing on, that will become my substrate. To that there will be an attacking reagent coming. That attacking reagent will attack the substrate. There will be breaking of bond. There will be some kind of reactions in between them. They will go to a state called intermediate. Intermediate is the transition state of the substrate and reagent. In the intermediate state, they will not be stable there. They have to lead to, or they have to go to a stable state. So intermediate state, there will be further rearrangement and they will give me the products as well as the byproducts, but the byproducts are not which I am focusing on. I'll be basically dealing with my products. Okay, this is how a general organic reaction looks like. Now if I'm having an idea about what general reaction looks like or what a general reaction might be taking place in any organic molecule, then I will also have to know that how this transition is going on, right? If I'm saying organic molecule is reacting with a substrate to give me an intermediate, but out of my curiosity, I'll also be wanting to know that what is exactly happening between the organic molecule or the substrate and the reagent so that they are going to the intermediate. What is the reason for reaction? At what site is the substrate or the attacking reagent is attacking the substrate? Okay. At what site the substrate is being attacked on, and at what speed the reaction is taking place. So basically, if I have to understand a chemical reaction, I have to understand at what site the reagent is attacking the substrate, how the reagent is attacking the substrate, at what speed the reaction is going on, because if I'm carrying out a reaction, that should be beneficial to me. If the reaction would be so fast or so slow, then that would not give me any benefit out of I cannot draw any benefit out of the reaction, and that reaction becomes a complete waste for me. Okay, so I have to understand the site of attack, the reactivity of the reagent and the substrate, as well as the rate of reaction. So all this, basically the sum of the exact path or how the reagents and substrate are going to the product side, all the study of this entire mechanism or the path of the reaction is called as the mechanism of the reaction. Okay. The study of entire progress of the path of the reaction is called as the mechanism of the reaction. Mechanism basically focuses on the rate of reaction, the stability of the products, okay, at what site the reagent is attacking, how fast the reaction is, whether it is thermodynamically and kinetically stable or not. Okay, these all information can be drawn from the reaction. And once I get a thorough idea about the mechanism of the reaction, then I can easily understand the organic reactions and I can draw a general summary of how organic reactions are actually proceeding. Okay, to understand the general way by which the organic reaction is proceeding, for that I have to know the mechanism of the reaction. Okay. So before knowing the mechanism of the reaction, what we all need to know is have to have some small concepts clear in our mind. Okay. If I'm saying any reaction, A is reacting with B to give C plus D. Okay. I'll be taking up this reaction. A is reacting with B to give me C and D. That means in A there will be breaking up of some bonds. In B also there will be breaking up of some bonds. Then those broken bonds combine with each other to form newer bonds, right? So in organic compound, what is happening? There will be breaking up of bonds. What bonds will break? I am saying organic compound means obviously there will be a carbon. Got it? So if I am saying a carbon is bonded to an atom X. Okay. Now, how this bond will break? Okay, of course there are hydrogen. If nothing is there, then hydrogen is obviously there. Now, breaking up of bond is called as fission. Okay, breaking up of bond is called as okay. Then for carrying out an organic reaction, bond fission has to take place. For carrying out of an organic reaction, bond fission has to take place. Now imagine a situation when you and your friend are holding a chocolate together. Okay. Then you have to, like, have you played tug of war in your life? Of course you might have. So what happens basically, if the two parties holding the rope together, if they are pulling the rope with the same strength, then what happens? A time might come, a situation might come, the rope might break in the middle. Okay, the rope might break. Suppose I'm saying, okay, rope will not obviously break, but let us take an example. You and your friend are holding a chocolate together. Okay, you both basically are pulling the chocolate towards yourself. Okay, you need to grab that chocolate. Now what will happen? Two situations might arise. The first situation is any one of you can come out stronger and pull the chocolate towards itself completely. Like you might be stronger or your friend might be stronger and will be pulling that chocolate entirely towards yourself, right? Or the situation can also arise where you and your friend are having the same strength and the chocolate breaks from the middle. Both of you get equal share, right? This can also happen. So basically I'm having two situations here. One, either the chocolate will completely go to one of the person, or the chocolate can be half, like broken down into half, so that both the person are receiving the equal halves, right? So same here, suppose carbon and this atom are holding the bond together. The bond is the chocolate for them, okay? They both are basically holding the atom together, holding the bonds together. Now, if one of them becomes stronger, then that particular atom will move out with the pair of electrons, okay? So in that case, the fission which has occurred is not occurring uniformly, is not occurring equally, okay? So that kind of fission is called as heterolytic fission, okay? That is called as heterolytic fission. Now, what do you mean by heterolytic fission? Hetero means different. Lytic means breaking down. Okay, lytic has come from the word lysis. Okay, so different way of breaking down means where the pair of electrons that were shared between the atom is not equally broken down, is not equally distributed. Rather, what is happening? One atom is coming out stronger than the other atom, and that atom is basically being selfish, takes up both the pair of electrons and moves out. Okay, that kind of breaking is known as heterolytic fission. Now, if both the atoms are equally stronger and they pull the bond together, then the bond, how the bond will break? Basically, one bond means two pair of electrons, right? I mean, one bond is a pair of electron, okay? Means two electrons are being shared between both the atoms. So what happens if both the atoms are equally stronger? Then what they will do? They will break this bond in the middle, okay? One atom will go with one electron and the other will move out with its one electron. So basically what will happen? There will be homolytic fission. That means equal distribution of electrons in the atoms, okay? I can call it homolytic fission. Okay, homolytic fission. Now homo means same. Okay, same or equal. So if there is equal distribution of electrons between the two atoms when the bond is being broken, that is called as homolytic fission. If there is unequal distribution, then that is called as heterolytic fission. Now in heterolytic fission, again two kind of situation are arising. First case, where suppose you are the carbon atom and your friend is the hetero atom or any other atom. Okay, now the case may be you are stronger, you are pulling the chocolate towards yourself, and your friend is not getting a bit of it. Okay, your friend is moving out empty handed and you are getting the complete entire chocolate. So what will happen? In between carbon and X, carbon comes out to be stronger, so carbon takes both the pair of electrons on itself and X is moving out without the pair of electrons. It is moving out sad without getting anything in return, right? So this might happen. And the next case, what might happen is you are weaker than your friend comes out to be stronger, your friend emerges out to be stronger, and your friend pulls the chocolate towards himself or herself and moves out. Okay, so basically then what will happen? You will become sad. You are carbon, now you are becoming sad because you don't have electrons with you left or chocolate with you. So here what will happen? Carbon, and in between carbon and X is coming out stronger and X moves out with the pair of electron, leaving behind carbon empty. So in both the cases, what will happen? See, in heterolytic fission, two conditions can arise where firstly the carbon atom can get the electrons or the X will get the electrons. Now, electron means negative charge. Okay, so remember, electrons means negative charge, and if I am saying one bond that is formed by sharing of two electrons, here I am talking about covalent bonds. Okay, one bond means two electrons. Now imagine if X is stronger, X is taking both the electrons. Okay, if I'm saying both the electrons, that means one particular electron, this electron is already belonging to X. Okay, this electron was of X only. So due to this electron, the X will not get any charge, any positive or negative charge, because that electron was belonging to X only, right? The extra electron which an atom gains, because of that extra electron only, the atom is having a positive or negative charge on itself. So if X is stronger, X is taking both the electrons with itself, then the charge developed on X will be due to this extra electron, not due to this, because this was the indigenous electron of X only. X was having that electron only. That electron was belonging to the family of X only. The extra electron which X has taken up was from the carbon. Therefore, if X is stronger, X is taking up electrons from carbon atom, then X is moving out with a charge of uninegative. Okay, X minus, and that minus was due to this electron, this extra electron which was not of X. Okay, not of X's electron. That electron was taken up from carbon and only one electron was taken up by carbon. So it is getting a -1 charge over itself. Now, if electron has moved out from carbon surface, then obviously you can see here two electrons are gone, but two electrons were not belonging to carbon. Carbon's electron was this one only. So as this electron moved out from carbon, carbon will get a unit positive charge. Okay, 1 unit positive charge due to the removal of its own one electron. Okay, remember this concept. The charge which a particular atom gets after losing or gaining electrons, that belongs to like the extra electron which the atom is gaining. For that it gets a negative charge, and if it is losing its own electron, then it's getting a positive charge. Okay, so here as carbon is losing this electron which was its own, okay, this electron had nothing to do with carbon. That's why the carbon is getting a +1 charge because of its removal of one of its own electron. Okay, so when the carbon atom, and obviously our center of study is our organic molecule, we are not bothered about X. So if X is stronger, X is taking away the electron pair from the carbon X bond, then one electron is going away from carbon. Carbon is acquiring a positive charge. In that case, the carbon has a special name. Okay, we know the atom which is losing electron forms a positive charge, and that is called as cation, right? that after losing electron, an atom gets converted to cation. Now here, what is the cation? Carbon is the cation. That's why we call it carbocation. Okay. We are taking carbon as the cation, therefore it is called as carbocation. Now if the opposite happens, like X is weaker than carbon, okay, X is weaker than carbon, X is moving out as X positive and both the electrons are remaining on carbon, then the carbon will acquire a negative charge, but that negative charge will be due to the extra electron given by X, not because of its own pair of own electron, but because of the extra electron which was given by X. Okay, so carbon here will get a negative charge. Okay, so this negative charge on carbon leads to the formation of a anion, right? An atom after gaining electron gets converted to anion. Here carbon is our anion. When carbon was our cation, we named it carbocation. When carbon is our anion, it is called carbanion. Okay, we are basically fusing the words together. Carbon as cation is called carbocation. Carbon as anion is called as carbanion. Okay, so here what happened? Carbon was having a negative charge because X came out to be weaker than carbon. X was not able to snatch away the electron with itself. So carbon turned out lucky. Carbon was having both the pair of electrons with itself. It acquired a unit negative charge on itself. Okay, it became a carbanion. Okay, so now if I'm giving you an example, let us understand carbocation and carbanion with an example. If I'm saying I had CH3X, okay, in both the cases I'm taking CH3X as an example. Initially what we have said is, if I'm saying carbon is having a tetravalency, carbon will form 4 bonds in order to be stable, and all the 4 bonds or the 4 bonded atoms to the carbon, they will be aligning themselves to the corners of a regular tetrahedron. So basically carbon, like if it is bonded to 4 different compounds, then the shape or geometry of the compound will be tetrahedral. Okay, the geometry will be tetrahedral, and in this case, in both the cases, what will happen? What will be the hybridization of the central carbon atom? Now, is carbon having a lone pair? No, carbon never has a lone pair. Okay, so what happens in all the 4 bonded state, carbon never has a lone pair of electrons. So if I see both the example, carbon is having 0 lone pair, and for calculating hybridization, I have already said we don't take pi electrons into consideration, although carbon is not having one pi electron at all, any pi electron at all, but we do not take pi electrons into consideration. What we take is lone pair and sigma bond. So if I see both the cases, what I see is carbon is not having any pi electrons, carbon is not having lone pairs, carbon is only bonded by sigma bonds. So how many sigma bonds carbon is having? 4 sigma bonds, right? 3 with hydrogen, 1 with the heteroatom X. So if carbon is having 4 sigma bonds, then the hybridization for carbon will be sp3. Remember, Z value for hybridization will be sp3. If you are confused with hybridization, you can go back to the lectures of chemical bonding. There you can have an idea about hybridization and you can come back here again. Okay, so if I'm saying this, then carbon is sp3 hybridized. Okay, and the shape of carbon will be tetrahedral. Let me take the first example, then I'll give you, explain the second one. So let us take a case. In the first case, what happens? Let us assume X is stronger. X will take up the electrons or both the electrons from carbon. It will move out. Okay, if X moves out as X minus, if X moves out as X minus, then we are left with CH3 plus, right? Now, if I see the hybridization of CH3 plus, isn't it appearing sp2? Because there are 3 sigma bonded electrons. Okay, the Z value comes out to be 3 here. because of the three sigma bonded like electrons are from 3 hydrogen atoms. So the value of Z here becomes 3 and the hybridization becomes sp2. Now remember, if I'm saying sp2, the shape of sp2 was trigonal planar. Therefore, the geometry shifts from tetrahedral to trigonal planar. Okay, what happens? Initially, they were tetrahedrally arranged, one here and other 3 here. Okay, 3 atoms, they were tetrahedrally arranged. But now what happened? After the removal of one, the heteroatom, all the 3 came to a one particular plane. Okay, they came to a one particular plane, and the empty orbital, that is the orbital from which the X moved out, that was perpendicular to the plane. Okay, that was empty orbital, that was perpendicular to the plane, and that's why it was available for attack. Okay, it was an empty orbital, it was available for attack, and all the 3 bonded orbitals, they came down to a particular or single plane. Okay, they become planar. So the geometry shifted from tetrahedral to trigonal planar. The geometry shifted from tetrahedral to trigonal planar, and the hybridization changed from sp3 to sp2. Okay, this was the shape and geometry of a carbocation. If I see a carbon neon, what is happening? X moves out without taking up any electrons. Okay, no electron is taken up by X, or I can say carbon was strong enough to pull both the electrons towards itself, and therefore carbon was acquiring a carbon negative charge. It was getting converted to a carbon neon, and X was moving out empty handed as a positive ion. Okay, so here X plus moved out and we have CH3 negative. Right. So if I look into hybridization, initially it was sp3. Finally, after the conversion into a carbon neon, then still it is sp3 because 3 bonded to hydrogen and 1 negative charge on itself. So negative charge can be, I can consider it equivalent to a lone pair of electrons. So what becomes the structure of this? Or if I say hybridization, then it was sp3 initially, and after losing electrons also, after losing the heteroatom also, it is in the sp3 hybridization. Now if I talk of shape, when it was sp3 hybridized, the shape was regular tetrahedron. Okay, like any sp3 hybridized carbon, it was tetrahedron. But after it lost the heteroatom, what happens? It gained a lone pair on carbon atom. And in base pair theory, I have already said lone pair bond pair repulsion is greater than bond pair repulsion, right? So the structure basically became a lone pair, like which is the negative charge, and 3 other hydrogen atoms were present. So instead of being the regular tetrahedron geometry, that became a distorted tetrahedron. Why? Because these lone pair repelled these bond pair with a greater force. The bond angle between hydrogen, carbon and hydrogen further decreased. Okay, so therefore the shape became a distorted tetrahedron. Okay, I can say from tetrahedron it changed to distorted the shape changed to distorted tetrahedron. Okay, not a regular tetrahedron. The symmetry was kind of disturbed due to the presence of or due to the emergence of the lone pair of electrons. Okay, so again, now what you have to see is one sec. Yeah, we'll be seeing degree of carbon. Okay, degree of carbocation, degree of carbon neon. So in order to determine the degree, first you have to see, we will be focusing on a single atom or a single carbon atom. If I'm saying carbocation, that means the carbon atom carrying the positive charge, right? So basically let us take the example of carbocation only. If I'm saying carbocation, that means C+. Now carbon is having 1 positive charge. It has to satisfy 3 other bonds. So if it is forming 1 bond, or it is having a bonded carbon atom, 1 bonded carbon atom, suppose CH3, CH2 plus. Now carbon atom is bonded to 1 single carbon atom. then its degree comes out to be 1 degree. I can say it is 1 degree carbocation. If carbon is bonded, or the select the carbon which is under study, if it is bonded to only one carbon atom, then it is 1 degree. If the carbon is bonded to 2 other carbon atoms, like for example, okay, here this carbon atom is under study and it is bonded to 2 other carbon atoms, then its degree becomes 2 degree. I can call it a 2 degree carbocation. If the carbocation under study is bonded to 3 other carbon atoms, then it becomes 3 degree. Okay. If the carbon atom then it becomes 3 degree carbocation. Okay. This is 1 degree carbocation, 2 degree carbocation, and this is 3 degree carbocation. Okay. So now we have like 3 different possibilities. It can be 1 degree carbocation, 2 degree carbocation, 3 degree carbocation. Now you have to compare the stability of 1 degree, 2 degree and 3 degree. Now for understanding stability, you have to understand 2 concepts. One is inductive effect and another one is hyperconjugation, which we will take up in the later sections to come. But for now, I remember the stability of carbocation is in the order stability of carbocation follows the order 3 degree, greater than 2 degree, greater than 1 degree. Okay, this is the stability order for carbocation. If I see carbanion, it is just the opposite of carbocation. If I say stability order of the order becomes 1 degree, greater than 2 degree, greater than 3 degree. Okay. So in this lecture, we had a discussion about what is carbocation, what is carbanion. In the upcoming lecture, we'll take up free radical. I hope this lecture was clear to you. Thank you so much for watching.